The name of this video is Force Between Infinite Wires. In fact, this is an example where we are going to use the result of the first video of this series of 3 videos on forces on circuits carrying currents, steady currents. This is actually a very important example. As a matter of fact, until November 2018, it was used as the standard for the ampere. And in fact, this experiment it was done a couple of 100 years ago, and so for 200 years it was used as the standard for the ampere. I will briefly mention what is used now towards the end of this video. So it's very important, and it gives a reasonable result, even though it's not exactly, of course, of what people have chosen as a standard later on. So this experiment is based on 2 infinite wires, which are parallel to each other and filiform and rigid. So 2 filiform, rigid, infinite wires with currents, each of which we have solved individually. In 242, we found the magnetostatic field generated by it by means of Ampere's law and symmetry arguments. And so this is our first infinite filiform, straight, rigid wire, and this is my second wire. These 2 wires are parallel to each other at a distance capital D from each other. So let us sketch, as always, first of all, a cylindrical coordinate system where the z-axis coincides with the first wire here. This is my z-axis, and this is my r-axis. This is the origin of this system. Clearly, u bar phi will have to go inward, so it has to be like this. We're going to make also another sketch to be more clear about that. So this circuit here, it's an infinite line oriented upwards, and I call it gamma 1. This one I call it gamma 2. Each of these carry a steady current. The first one carries a steady current I1, and the second circuit a steady current I2. The distance between these 2 circuits, which again are parallel to each other, is capital D, is the distance between these 2 circuits. And eventually we're going to consider a length capital L, which will be much larger than capital D, in order to use all the results we have seen for infinite straight lines previously in 242. So this is the scenario. Okay, let me also remind that these are filiform and rigid wires. So clearly only effects of the external field, of any external field on each of them are important because they're rigid and they're filiform. So we can use the results of the very first video we have done here. So let's look at this sketch from above, so that these are the traces of the 2 currents. So this is the trace of the first current, this is the trace of the second current, and they are at a distance capital D from each other. So this is my distance here, capital D. I'm looking again at this sketch from above. So when I do that, this is going to be my r-axis as always. In this case, z points in this direction, and in this case, bar phi points in this direction, right-hand rule, and it starts from 0 here. So this is my bar phi in this fashion, okay? And here, again, we have the 2 currents. This is the current I1, the trace of I1, steady current, and this is the trace of I2, also steady current, okay? So the question we want to ask in this limit here is, what is the force acting on the second wire 2 due to the first wire because of a length capital L on the first wire, okay? Which again is much larger than capital D. Of course, it's not to scale here. Just for pedagogical reasons, I had to do it larger here so it looks nicer. All right, so this is the question. So that's what we want to compute. And on your own, you can compute the other way around if you want, the force from 1 to 2 according to L. This one is something which you can do, for example, in Piazza as a question. All right, let's focus on this one for now. So we use the definitions, the equation we derived in the first video. So we know that for a filiform wire carrying a steady current, F is given by the circulation along the entire length gamma of the wire of I, the steady current, times the L, T vector B naught, because the wire, obviously, we are saying is rigid, so it's not flexible. Okay. Now, what is the field B naught in the specific case considered here? B naught is the external field really due to the gamma 1, so it's going to be from 242 mu naught times the current I1 divided by 2 pi small r in general times u var phi. Remember that this eventually will be capital D because the second wire is where I want to calculate the force on, and it is at a distance capital D. What about I? Okay, here people make usually mistakes. I1 is that it generates the external field into which this gamma 2 is located, but I has to be, since I'm looking at the force F21L, this I is actually I2. Okay, so be careful, I'm just mapping all these letters to this specific case. Again, what about DL? Well, DL is clearly DZ, because the only direction of gamma is DZ. T is equal to UZ, because again, we are going in the Z direction. B naught, we already wrote it down here. And also this line integral, the line integral actually becomes very simply the integral over gamma for infinite lines. It's a special case, okay, where clearly we cannot do the circulation because it's an infinite line. So we need to do it just over the length. It's not a, well, of course it's a circulation if you want, but it's more proper to write it as like in this fashion. Okay, good. So now that we have all this mapping done, we can finally rewrite this force F here. It's mostly constant, so we cannot take all of them outside the sign of integral. What I is I2. We take it outside, steady current. What about DL? DL, we need to keep it. What about T? T is the direction, which is UZ. What about B naught? B naught is all constant, so it's crossed U var phi from B naught, mu naught, all constants, times I1 divided by 2 pi. R becomes capital D in this specific case because we are considering the force on this wire, which is a distance capital D, as I already mentioned before. U var phi we already took into account here. So I, we have it. The L is the Z, we need to use it. T, we have it. Of B naught, we have U var phi, mu naught divided by 2 pi D, and we specify for D because we are at that distance, not to make that mistake. Integral, let's do it only on a length capital L, which is much larger than D, dz, which is a trivial integral left to be done. So clearly the result of this equation eventually is nothing but, what is uz cross u var phi? Well, this is, you need to be careful because it's the usual trick here. So we are doing, if this one is tangent unit vector u var phi, this one is uz. Clearly this cross product is minus ur. So you need to be careful with that. So you get a minus mu naught over 2 pi, which are fundamental constants. So this we have it, I1 times I2. The integral gives me capital L divided by capital D. So this gives me minus 1. I2, I1, we have them here. mu naught over 2 pi, we have them here. D, L over D is from this quantity here. And this has to be directed as UR. Is minus UR, because this is minus UR. Right there. Okay, great. So this force is attractive if the two currents have the same sign, and is repulsive if the currents have different sign, opposite sign. And again, until November 2018, which is actually the day I taught this in 2018 during a 342, interestingly enough, exactly until that day in November, as it turns out, this was the old definition, the old standard for the ampere. So it's ampere A, or if you want, small a, ampere standard. And what that standard used to recite is as follows. It told us that you need to make an experiment, which of course is a little bit tricky because what is L much larger than D? You need to be able to do it, proper experiment as an experimentalist or a metrologist. And so then you want to say that the 1 ampere is the current, the steady current, required on both wires, 1, 2, such that on the second wire or first wire, they will be the same. There is a force density F per unit length, which in our case is nothing but the absolute value of F to 1 capital L divided by L, for L much larger than D, of course, and D we assume that is 1 meter. Okay, so you need to choose how long is L, but not prescribed, as long as it's much larger. Usually I would say 100 meters, 10 meters, you need to decide what gives the lowest, the smallest error. And so this force has to be 2 times 10 to the minus 7, since it's Newton, but divided by meter is Newton meter minus 1, because I'm going to normalize over L. Okay, and so if you do the calculation, as a matter of fact, that's what you get. So let's do this calculation together quickly. So if you do mu naught, absolute value minus doesn't matter. So we have 4 pi times 10 to the minus 7. This is my mu naught. The units, I will put it somehow here on the right, divided by 2 pi. Mu naught as units of Henry divided by meter. Then I need a distance of 1 meter. So I divide it by D, which is 1 meter, as prescribed by the experiment. And then I need 1 ampere times 1 ampere. So 1 ampere times 1 ampere, which is ampere square. And so when you do this calculation here, you will notice that pi and pi goes away, 2 becomes 2, so effectively you get 2 times 10 to the minus 7, and this one, if you put it in Wolfram alpha, is actually Newton meters minus 1, which is exactly what is prescribed by this experiment. And so to summarize this video, this is a very important example because it was used for a couple of 100 years as the standard for the ampere. It's the force between two infinite wires, filiform and rigid. Gamma 1 and gamma 2 with current, steady currents I1 and I2. We want to find the force on the second wire 2 due to the first wire 1 for a length capital L much larger than the distance between the wires. In the cylindrical coordinate system, we use the equation we found in the first video, but for infinite lines. We find B naught, which is due to the first wire. You could call it B gamma 1, whatever you like, which depends on I1. I in here is obviously I2, the L is dz, T is uz. You plug it in, the integral is trivial. Note that there is a minus sign, which means attractive or repulsive depending whether these are same or opposite sign. This was used as the definition of the standard for ampere for a couple of 100 years until again 2018. Now, people are using the so-called quantum, you can look at NIST, is the quantum metrology triangle, which connects voltages, currents, and charge and frequency, if you want as well. And all this triangle is based on the Josephson effect, which is actually what I work on in my lab, and the quantum Hall effect, which was discovered by Klaus von Klitzing back in the Technical University of Munich, where I've done my PhD. And then eventually the single electron tunneling as well is part of the game, which has been strongly studied by the Chalmers group from my former supervisor, Per Delsin there. And so you can look at NIST to see all this triangle, which connects together all these basic elements to define ampere, which now is defined basically from the definition of electron, effectively. That's it.